Primary support for Earthlings 2.0 comes from Technica Communications, an award-winning PR firm amplifying breakthrough technologies of the future. Additional support comes from Tigo Energy, solar energy and software solutions provider focusing on commercial, industrial, and residential solar installations.
Sometimes I hear people, who are skeptical about hydrogen, and they're like, hydrogen, we'll never see hydrogen. And I'm like, you're not wrong, right? The average person today actually never sees diesel too.
Greetings, Earthlings, and welcome back to Earthlings 2.0, the show where we imagine how we could be better versions of ourselves and build a collective future we actually want to live in. As the world continues its efforts to decarbonize, hydrogen is emerging as a pivotal element in the energy transition, especially when we're talking about transportation. And the heavier the transportation, the more hydrogen can decarbonize that sector. However, the widespread adoption of hydrogen has been hindered by some technical challenges, and this relates to durability, cost, and efficiency. So, when it comes to fuel cells, now those are the devices that convert hydrogen into electricity without burning it, and the only output is water as a waste. And then you have hydrogen electrolyzers, which is basically a fuel cell running in reverse. And those are the devices that make hydrogen from water. These current offerings often struggle with durability because hydrogen crossover can inadvertently cause these side reactions that can lead to degradation of the membrane or the catalyst layer or other components in these devices, causing them to fail. So, our guest today says addressing these issues is critical for integrating hydrogen solutions across various sectors, and he thinks he's figured out a solution to fix it. But before we get there, I'm your host, Lisa Ann Pinkerton. I'm the CEO of the award-winning tech PR firm Technica Communications and the founder of Women in Clean Tech and Sustainability. Before both of those roles, I was an award-winning environmental science, health, and education reporter and general tech reporter for NPR and PBS. And we appreciate each and every one of you Earthlings for tuning in with us today. Welcome. If you're a returning listener, thank you for coming back and listening to this show week in and week out. We deeply appreciate your loyalty. And if you're new, welcome. Have a look around our feed. We've got a lot of different topics here, from climate tech and clean tech topics all the way to the energy crisis, autonomous vehicles, lab grown meat, you name it, we have covered it. And you can learn a lot from listening to our feed. If you're a longtime listener and you want to get more out of the community we're building here, please feel free to join our Substack newsletter. You'll get a 1-month digest of what's been happening with the show. We also have a listener survey. We'd love to hear your thoughts on the show and how we can make it better to suit you. And finally, if there's one thing you can do for the show, is share it with your friends. The next time you're talking podcasts or you're talking about a topic that you heard on the show, feel free to cite us and let your friends know that this is a good podcast to listen to, and that's how we're going to grow our audience. And thank you to Resource Labs for having us on the network. Now, today's Tech Spotlight is with Celadyne Technologies. They have developed a low-permeability membrane that significantly enhances the durability and performance of both fuel cells and electrolyzers. And so this might sound a little wonky or in the weeds, but don't worry. This conversation that we're going to have today is focused on making these concepts simple to understand and also talk about later when you're, at that, virtual water cooler in the Zoom room waiting for everybody else to show up. Without further ado, I'd like to introduce our guest today, Gary Ong. He is the founder and CEO of Celadyne Technologies. And before founding the startup, he participated in the Breakthrough Energy Fellows program and was a fellow at the Argonne National Laboratory. So we're catching up with him from his office in Chicago. Welcome, Gary, to the show.
Hi, Lisa.
So before we get into what you're doing at Celadyne and what you've developed, could you walk us through some of the pitfalls that fuel cells and electrolyzers can face that is holding the technology back?
Of course. So when I think of fuel cells and electrolyzers, right, I think of it as imperfect technology that was first invented in the 60s, right? Kind of a quick history lesson to the audience, right? Like fuel cells and electrolyzers in its current form didn't really exist until the space program. We actually invented fuel cells and electrolyzers because we had to get to the moon. And we used it. The Gemini program, I think, had a fuel cell that we powered. We used the fuel cell to power it to get to the moon, right? And after that, you see all the press releases about, wow, this works. We're going to have hydrogen cars and everything in the world, right? And it didn't happen, right? Because it turns out it was easy to invent the technology, but it was much harder to perfect it, right? And one of the inventions that enabled all of this technology was this membrane called the proton exchange membrane, invented in the 70s. And believe it or not, the one we're still using today in most modern devices is basically a variant of that technology. So, and it's not because people haven't tried to improve on it. It's really hard to improve on it. And one of the things that we think we've done is being able to finally change that. But the beauty of it is, when you improve that thing, you get a dramatic improvement in all the performance characteristics of these devices, because these devices intrinsically rely on this almost magical material to work in the first place.
That's fascinating. So tell me a little bit more about how a proton exchange membrane works.
Let's think about it this way, right? When I think of hydrogen, I like to simplify. I'm like, okay, what is it? It's a gas that has energy in it. You need to open it up and release the energy. One option is you can burn it. Probably not want to burn it. It's a combustible fuel. So if you don't want to burn it, then you have to run it through this thing called a fuel cell. Ultimately, if you want to make it, you have to use this thing called an electrolyzer. So when you're thinking about how a fuel cell has to function, if you don't want to burn it, you probably don't want the hydrogen to meet air or see air, like oxygen, right? So now, intuitively, your brain goes, well, if you don't want the hydrogen to see the air, what do you have to do? You have to block the hydrogen. And this thing also has to block the air. But if you block both of it, then the hydrogen and oxygen cannot react. So you have to have the hydrogen somehow meet the oxygen in a safe way. The way that happens is that the hydrogen actually breaks down on a catalyst into something called a proton, hence a proton exchange membrane, right? And then the proton moves through the membrane to meet the oxygen on the other side. And the proton, which is a single hydrogen atom, meets with the oxygen to make water, H2O, right? And that's how it is safe. Now, when you break the hydrogen down into hydrogen, the proton, there's actually an electron that comes out of it. So right there, then and there, intuitively, right, you can kind of get a sense that the membrane has to block gases. It has to let that proton through. But you also have to block the electron, because if you don't block the electron, you just get an electrical short. What you want is to block the electron so the electron goes through an external circuit, which is your light bulb. So if you just go with your simple intuition, right? You're like, okay, I need to block gases, I need to let protons through, and I need to block electrons. That's it. That's the three fundamental properties of a proton exchange membrane.
Yeah, the vision that's coming to me is like a molecular, like a nightclub, and there's a bouncer, and he's letting the right things through and not letting the other things through.
Exactly.
When it comes to the technology that you've developed, you call it a low permeability membrane.
Yes.
What makes what your membrane is able to do different than what's traditionally used?
So traditionally, right, the most membranes today are built upon a Teflon backbone. Believe it or not, it's the same Teflon you would find in a pan, right? You take that Teflon, and then after that, you put these things called cation groups and anion groups on there. These are just think of them as just charged points, okay? And once you do that, now you basically have Teflon that is functionalized. Here's the problem with Teflon, right? You ever notice? So I'm sure you're familiar with Gore-Tex.
Yep.
Right? It's a very breathable material, right? What does breathable mean? Lets all the gases through.
Yes. It's not a very good bouncer.
Everything goes through it, right? But that's literally it. So it lets all the gases through. Now, it's not terrible in that sense, that such that you cannot make a device, right? It's good enough that it's still letting the protons through. It's still blocking some of the gases, right? And it's good enough to make the first devices. That's why I keep saying it's not a perfect device, but it will function. Imagine now if you have a material where it's like you can actually block all the gases, still let all the protons through, block all the electrons. Okay, when you do that, right? Effectively, the innovations on a new polymer that is not Teflon, right? Get about 50% to almost 10x better depending on how you do it. Now you can block all the hydrogen, and now you only let the protons through and you block the electrons. What does that do to you? If you block all the hydrogen, you will shut down any side reactions that hydrogen is reacting with oxygen in an uncontrolled fashion that you don't want. And it is actually those side reactions that causes degradation in a fuel cell. If you're like, what is it making that's making it degrade? It's very simple. Very simple chemistry. Hydrogen plus oxygen gives you hydrogen peroxide. Hydrogen peroxide, literally the thing that you use.
To disinfect things.
Yeah, you like to use it to design things. In the case of a fuel cell, that thing will chew everything else up. And then suddenly you get pinholes on the membranes, your catalysts start degrading, this, that, whatever starts corroding, and you're like, this is all bad news. I don't want hydrogen peroxide. Not in this case, at least.
Yeah, because oxygen is very corrosive.
Correct. That second oxygen from hydrogen peroxide is it's very bad.
And it breaks the cell walls. And that's how it's able to disinfect things.
Yes. And in this case, it'll break most chemical bonds if you let it.
Yeah, well, my dad's going to be so excited to listen to this episode. He's an analytical chemist, so he's going to be very proud of me for understanding this chemistry. So this low permeability, this is kind of the technology innovation that you're bringing to market. And you were telling me that it can work both for a hydrogen fuel cell as well as an electrolyzer, and that's not something that you originally set out to do, but it was a beneficial happenstance that you recognized that you could use this for both.
It's in the design of a fuel cell and electrolyzer because they're so similar that when you innovate on the material set of one, you will impact the other one too, right? So in the case of for us, right, we were focused on innovations on the fuel cell side because we were very aware of what the materials needs were. And then later we looked over on the electrolyzer side and realized if I thought the fuel cell people were using old materials, the electrolyzer people were using materials that was developed in the 80s. And then now it's like, oh my gosh, I guess might as well translate both of them to state of the art materials. And it turns out when you do that, suddenly all the efficiency curves and durability curves get way better on the two sides. So we knew they would be relevant. We just didn't expect it to be so relevant. and but that's what I mean by we got lucky.
It's like you're taking floppy disk technology and transforming it into a solid state hard drive. Like sounds like that's the innovation leap that we're talking about here.
Yeah, it's a big leap, right? I think when you think of, kind of give you some concrete numbers, right, with our technology, right? Right now, if you think of trying to invent a fuel cell truck, right? I want to move goods using a truck that doesn't emit any emissions and only outputs water, right? If you don't have our technology, the fuel cell truck will break in 4 years. And then a diesel truck will survive 15 years.
Or longer if you take care of it.
So if you look at it from a simple economic standpoint, right? When people say, oh, fuel cells will never happen because the technology sucks, right? And I'm like, even as a hydrogen enthusiast, I'll tell you, you're right, right? I can't argue with the science. But the difference is from our standpoint, right? As a technologist, we look at that and we say, there's something we can do about it, right? Nothing in science says it should only last 4 years, right? So if you fix it with our technology, we quintuple durability, which means we can get it to last 15 to 20 years. And that basically suddenly makes your technology viable. And that wouldn't just make it viable in things like trucking, right? It will also make things viable in things like shipping, rail, aviation, or anything I think of where you will have something and plan to use it a very long time, which in this case is most industrial applications, not light duty applications like consumers, right? We would, I think the average American changes a car every like 5 to 10 years. I guarantee you, if you're a truck driver, you do not change a truck every 5 to 10 years. So that's the focus, right? Hydrogen, I think, at the end of the day, sometimes I hear people, who are skeptical about hydrogen, and they're like, hydrogen, we'll never see hydrogen. And I'm like, you're not wrong, right? The average person today actually never sees diesel too, right? How much of your life is impacted by diesel? Not very much, unless you really think about it. Then you start realizing everything you use in a day-to-day life is moved by diesel. Everything you use that is made in some way, shaped by diesel, right? And what I believe is, well, diesel and natural gas, right? And what I believe is that we're at this moment in history where we have a shot to basically transition hydrogen to make the new industrial fuel, replacing diesel and natural gas for heavy industries.
That's a great vision. Thank you so much for explaining all of that. Is this lack of innovation in the membrane one of the reasons why we've sort of watched the hydrogen market kind of just lumber along and not really gain the adoption that we saw in solar or energy storage or even EVs, frankly? And like it's always been like this almost like a sleeper of an industry.
Yeah.
Would you attribute that solely to the membrane or to other technology innovations, as well that are lacking?
In the case of comparing hydrogen to solar to wind and then to batteries. So full disclosure, when I did my doctorate, I actually spent half my doctorate working on advanced battery technologies, and then I switched over to hydrogen once I realized that like battery technology wasn't going to be sufficient for us to fully fix the world. I was like, and then at the time I was like, there's already 500 people working on batteries at least, and then there was like 100 working on hydrogen. I was like, okay, shots on goal. Maybe I should switch sides and try to do something about hydrogen instead. Right. Basically, I was like, I don't think batteries need me. I think hydrogens need me more. So, sidebar, right? To answer your question, around 2000, right, leading up to before Elon started Tesla, if you chart the progression of batteries and hydrogen, they're actually kind of about the same, right? There was no electric vehicle that's a battery vehicle that's reliable, right? There's no hydrogen vehicle that was very reliable at the time either. Battery technology wasn't great. You couldn't really use it to power anything bigger than, like, say, the cell phones and so forth. Even the golf carts were still gas powered or diesel powered.
Yeah, laptop batteries. That's why Elon used laptop batteries and chained them all together for the first Teslas.
Exactly. So it is 100% to Elon's credit, right? That like he put together the batteries and everything and made people believe that this could work with batteries. And then since then, from 2000s, I think Tesla was 2000 something, right? Around the early 2000s. And then I think 2008 onwards, it was almost like 10, maybe 15 years of effort. And then now you start seeing EVs adoption and people go, oh yeah, look, it all works, right? But people forget sometimes there was a time in history around 2004, 2005 where everyone was like, no, EV is nonsense, blah, blah, blah. It's the same thing all over again, just 15 years of effort later. And now it, no one questions that anymore, right? Now with hydrogen, have we had 15 years of concerted effort to make it happen? I don't think so, right? And now you look at wind and solar. If you remember, solar went through a complete bust in the US after '08, around 2011, 2012 or something. And everyone said it was the death of solar, right? But the industry chugged on. And guess what? 2008, 2010, and now 2023, 24, look at the rise of renewables. Everyone everywhere is installing solar panels. 15 years, right? So I think it is a matter of time when it comes to if you put in, steady energy and steady effort for most of these technologies, that reality will kind of catch up and the technology catches up and it will work, right? Because fundamentally, everything we're doing, we're not violating the laws of physics, right? It's a matter of concerted effort. So when I look at hydrogen now, when I started the company in 2019-ish, right, when I started working on it, I told myself, right, I looked at batteries and I looked at wind, I looked at solar, and I was quite convinced. I was like, 2020, 2019, gave it 15 years, 2035. I think I can make this happen, right? 2035 is where I was like, the world will be convinced that this will happen and market forces will take it away, right? I was like, up until 2035, you need to champion hydrogen, you need to put in incentives, you need to make technology work, etc., etc. But circa 2035 onwards, market forces will take it. In some ways, your competitors will try to copy what you're doing, but that in some ways is the whole point, because that's how you actually transition a whole world towards something new.
I guess I was trying to figure out too, like, beyond membranes, are there other aspects of a fuel cell or an electrolyzer that you feel are similar in this scenario using 1980s technology and it hasn't yet been advanced to the 21st century?
So I'll answer that from a more scientific standpoint, right? Um, the beauty of an engine, right? When we first invented like a combustion engine and we tried to improve it, is that we were able to make steady improvements, increase the efficiency of engines and everything. My dad was an automotive engineer, so I love engines. Um, but if you ever open up and see an engine, it's like a thousand parts, a thousand moving parts moving in symphony. It's brilliant, right? But the beauty of a thousand moving parts is you have a thousand different knobs you can twist and turn to make it better. A fuel cell or electrolyzer fundamentally has four components. It has a membrane, it has a catalyst, it has a porous layer to distribute gases and water, and it has this thing called a dipolar plate, which is literally just metal that you sandwich together so that you can make a circuit. Four components. I tell people sometimes it's the equivalent of saying, go make me a dish, and this is a four-component spaghetti. Oh, and by the way, the tomato sucks. Go make me a amazing pasta dish, and you're like, I don't know if I can, Gary. Like, you only have four things here, and you already told me one of it is bad, right? So to answer your question, right? So you can't really change the conductor because that's just steel. The porous layers are actually this porous carbon, so you can't really change that either. The catalyst you can change. That is the almost infamous platinum catalyst that everyone talks about. And now in the case of electrolysis, they talk about iridium. That you can change, and people are trying to change it. And the last one is the membrane, right? But more people have tried to change the catalyst than change the membrane because the membrane has been so difficult to change, right? The catalyst is actually slightly easier because with the catalyst, what do? You look at the periodic table and you throw the kitchen sink at it. I'm like, one of these things or any kind of permutation of this should work.
The Thomas Edison style of invention. Let me just go through hundreds of things, and one of them's eventually going to work.
Right. And but the good news is that field has advanced a lot on the catalyst side. So now most of the time, right, the catalyst is actually less of a concern. Like I have some people come to me sometimes, they say, oh wow, the catalyst is still really, really expensive, right, for fuel cells. But if you look at the numbers, you'll find out very quickly that the amount of catalyst you'll use in a fuel cell these days, it's actually almost comparable to the amount of platinum that's in a catalytic converter. So if you don't complain about the amount of platinum in your catalytic converter, you shouldn't need to worry about the catalyst in the fuel cell. But on the membrane side, right, you're like, okay, has there really been any innovations there? And by the way, right, here's another reason why the membrane is critical. Okay, sorry, now I'm going to go into a design class on how to make a fuel cell. Hopefully that's okay, right? You start by picking a membrane. Once you've dictated the membrane actually dictates what catalyst you can use. So once you've chosen the type of membrane you want to use, you actually have to use certain kinds of catalysts and certain amounts of catalysts. It also dictates what porous transport layers you have to use, because that one is responsible for hydrating the membrane. It also dictates the durability of your device, because once the membrane forms a pinhole, this thing is dead. It dictates the permeability, which is the crossover, which I've talked a lot about durability and side reactions. If you have a side reaction, necessarily it means that whatever hydrogen you have, you're not using it as fuel. It's just going around the back door, which means it actually affects efficiency, right? You see where I'm coming from now? Why when you change the membrane, everything else changes?
Yes, and that would also be a reason why you wouldn't want to touch the membrane because now you've got to change everything else.
Correct. So the other thing is like when you change the membrane, right? A, it's really hard to change it. Number two is once you change it, right? There's both a lot of potential for improvement, but you can also get scared, right? And one of the things that we have done on the Celadyne side is not only did we change the membrane, we actually made the membrane completely drop in. It was a 1.5-year effort to make it drop in. And here's how we actually proved to ourselves that it was a true drop-in solution. We bought a fuel cell, took it apart, put our membranes in it, stuck it back together, and saw that it ran.
That's really cool.
Yeah, in engineering speak, you don't ever do that. But we're like, we're engineers and we're like, we can convince everyone that it's drop in, show people the data. But what's the most realistic drop-in test you can possibly do, right? I remember buying the fuel cell from the vendor, and they're like, "We strongly advise you do not open this fuel cell, because we strongly believe that once you open this fuel cell, it will no longer function."
You're gonna void the warranty, Gary. What are you doing?
Yeah, it's like 10 grand, 10, 20 grand down the sink, right? And I was like, "Yeah, but you have a bunch of engineers here, and if you want to prove to someone that it is drop-in, what do? Open it up, drop it in, right? It's the most aggressive test." So we did it, and the thing ran. It actually matched all the theoretical predictions that we did, and that's when we were like, "This is true drop-in." So then when you enter our customers, they're like, "Oh, I don't know if I want this thing because I'm gonna have to re-engineer everything." And I'm like, "No, actually, check this out. You don't, because we already spent 2 years of our life trying to make this so that you don't have to re-engineer every other thing, right? It's a beautiful thing where you can make something that just integrates the same way, but fundamentally actually has very different performance characteristics for the people that we serve."
That's very cool. I'm happy to hear that you did your own field research, if you will, to prove that this was going to work. Because that leads into my other question, which is, who are your customers? Are you selling to the fuel cell and electrolyzer companies, or are you making your own fuel cells and electrolyzers to sell?
So right now, our ongoing traction, we actually have a contract with General Motors, where we're selling them materials, these membranes, right? We also have a contract with the U.S. Army, where we're selling materials to an external contractor who's then integrating it into fuel cells for the U.S. Army. I can talk about all this because it's public. And then on the electrolyzer side, we actually finished a pilot with National Grid, out in the Northeast. And it was a very small pilot to make hydrogen production related to using hydrogen to decarbonize natural gas, right? But to answer your question, most of our revenue we get from selling membranes and selling materials. And on the electrolyzer side, I think if the right partner comes on, we'll be interested in partnering with an electrolyzer company. But right now, just because of necessity, we've already built electrolyzers. Because again, kind of going back to, how do you prove if something really works in an electrolyzer? Well, you have a group full of, you have 12 engineers in a room. What do? Built an electrolyzer. So we've already built the electrolyzer. So we have the option to sell electrolyzers if we want to. I think now it's just a matter of what the market demands. Is it more electrolyzers or is it more membranes? And after that, we can go from there.
It sounds like more membranes because, what do they say? You make more money selling shovels than you do searching for gold.
Yes and no. But I think right now on the fuel cell side, absolutely. Right. The market is really mature. There are a lot of people making fuel cells, and we think we can make a bigger difference in the industry by selling membranes and empowering those devices to work better. Right. On the electrolyzer side, I think there's some market discovery still to be done, to really understand who's making the right electrolyzers. Right. Because right now, I think when people think about electrolyzers, they think of electrolyzers as this device that just makes hydrogen, and all electrolyzers are effectively the same, right? And there are actually differences in terms of how an electrolyzer is designed beyond the material set. And it dictates basically how easy it is to, kind of put an electrolyzer into a steel plant versus an oil and gas plant versus a chemical plant and so forth. And that's, I think, part of a broader conversation of how to do partnerships and making sure that whoever we decide to work with is actually building the right thing. Because now going back to startup strategy, right? If I sell our materials and so forth to someone and empower their technology, but if they built the wrong product, both companies will die, right? And then the worst one would be that means this technology will not see the light of day.
When you say right type of electrolyzer, what is quote unquote the right way to build one?
The right way to build one should be an electrolyzer that can truly integrate with the grid, so that when a solar or a wind farm generates a lot of excess electricity, this electrolyzer is able to directly take that energy and convert it into hydrogen. And then when you don't need it, right, that electrolyzer can effectively go back down to low, basically almost no operation, right? And one thing I haven't really talked about, which now again goes back to the membrane, right? So it affects durability and so forth. Turns out in electrolyzers, it also affects safety. So if you try to build an electrolyzer right now, and if you don't have membranes that are really low permeability, or at least in some ways prevent hydrogen from crossing over, right? When you run a electrolyzer at high currents and you generate a lot of stuff, right? Turns out, believe it or not, it is actually safer. Why? Because you're generating hydrogen on one side, you're generating oxygen on the other side, right? So you have a lot of both gases, right? And don't forget, there's always this thing called hydrogen crossover we just talked about, right? You have a lot of gas A and a lot of gas B, and let's say even if a small smidget of that 1% of that gas crosses over into the oxygen stream, it doesn't matter. It's 1% out of 100. Now, okay, now let me slow it down and bring it down almost to no generation. But turns out the amount of hydrogen crossing over the membrane is the same number. So that 1% is now suddenly 10% going into the oxygen stream, right? So now if you have a 10% hydrogen stream in oxygen, instantaneously, that is something that's like, OSHA will shut you down so fast that it's unacceptable. But 10% hydrogen and oxygen is actually a flammable mixture, right? It is very dangerous, right? So now, if you think about that, so now imagine our hypothetical electrolyzer and you couple it to a renewable energy plant and you say, go ahead, ramp it up and down. Yeah, when it's high, you're like, it's very safe. When it's low, depending on how you ramp it down and what material sets you use, that can be the difference of between making a bomb or making something that's very safe. And so that's where the electrolyzer design comes in, right? And it's like, if you have the amazing materials, right, it changes how you can design these electrolyzers. And one worrisome thing in a nascent industry like electrolysis is that you send materials to an electrolyzer company, right, and they don't end up building the devices in a way that meets its full potential, right? Whereas with the fuel cells industry, General Motors, Toyota, and the likes, right, people who we work with, they've had decades of experience working with fuel cells. So when we send them materials, we get their data inside. It is very obvious from us that we're like, we don't need to do that heavy lifting. They are already maximizing the potential of the materials, right? It's like it's better in their hands. Sorry, slight side anecdote on this, right? One of the craziest things that happened to us in circa 2022 when we first started shipping materials to OEMs. I cannot name them because of NDAs, but there were two. We sent them materials, shared data with them, and then 2 months later, they came back with us and sent this data, and we're like, how in the world did you get this data? It was better than our data by a lot. And we're like, do we just not know what we're doing? In some ways, it was true, right? They were better than we are at building fuel cells. Now, they sent 2 sets of data, right? First, it was the materials data, which you're like, oh, it's matched. Then they built a fuel cell with it and was like, oh, check out this amazing fuel cell that we could make with your device, with your materials, right? And we were like, oh, I remember talking to my team going like, should we tell them that we actually built a fuel cell, but that fuel cell wasn't nearly as good? Oh no, we just stick with the materials part of it, right? And they're like, yeah, let's go with that, right? You know?
Like, I need to find out who built that thing and like meet him at a conference and take him out for a drink and get him to spill his beans on how he built this thing.
Well, here's the best part. The fuel cell industry, most people don't realize, is actually quite friendly. Because the fuel cells went through a lot of hate around circa 2005, right? And then with the batteries happening and everything, there was just a lot of, kind of people who were very negative about fuel cells, right? So, but because of that, the people who have been in fuel cells, who have been working on this for like a decade and so forth, we're still here because we actually want to see the industry happen and the technology happen. So it's a rather helpful community. So guess what, right? With that really, really awesome data and everything, after they shared it to us, we asked them how they did it, and they told us.
Well, that's cool.
Yeah, they just told us. They're like, oh yeah, no. Turns out your material, when you do this to it and use this catalyst, it behaves way better. And if you like do this weird post-processing into it, like it becomes much better. They didn't know the chemistry, so they didn't know why the post-processing works, but we did. So I was like, oh yeah, that makes a lot of sense. So then the performance got better. It was quite collaborative, right? And that, is the difference, right? So for electrolysis, for instance, to give you an example of like a partner conversation, if you were working with, say, an electrolyzer manufacturer, right? Right now, I think electrolyzer, the field is just very competitive. So if you try to work with an electrolyzer manufacturer and you send them materials, more often than not, the response is going to be something like this: send us your material, we'll test it, and we'll tell you if it's good. And we're like, well, will you tell us more? Like, can you say? And they're like, no, just it's like a black box, right? In part, I understand because of the competitive pressures, but it's a different thing, which makes it a little bit more difficult to work with, right? But I don't know. I'm hopeful. Maybe we'll find the right partner, right? And then maybe that would be a viable business strategy. But as of right now, we'll focus on selling materials and building slightly bigger electrolyzers, if for nothing else, to de-risk this thing and the implementation of electrolyzers. And if I get a customer to buy it, then I guess we're selling electrolyzers.
It sounds like you have a lot of opportunity, and you have this membrane that can serve various purposes, which is great for a startup business because you can really focus in on the thing that's going to give you a good runway of revenue now, and then build the second one when it's ready. You execute on that, and then you've got two streams of revenue. So I think you're setting yourself up well to have longevity here.
Out of necessity, though, could we have built an electrolyzer business early on in 2019, 2020? Possibly. I mean, I'm a first-time founder, so definitely don't have the clout to raise $1 billion. It's just on my word, right? So it would have been more difficult to build an electrolyzer company and try to do that first time going round. Number two, even if I had done that, COVID was in 2020 and we survived it without raising any venture capital funding, right? So a material strategy was a early revenue first strategy that the company could execute on with a subsequent device or electrolyzer growth strategy, right? And that basically lets you create, exactly like you said, a multi-revenue strategy for companies, at least in Celadyne, for this company, right? That hopefully will be more sustainable and have long longevity for the company future.
Oh, so my last question for you is, we're a futurology podcast, and I love to pick people's brains about what they can see in the future, knowing what they know and the work that they do in their industry. So I heard you say that 15 years of development is what carried solar to being a mature technology, and we just haven't seen that yet in hydrogen. So what do you expect to happen in the next 10 to 15 years as this industry is developing?
I think 2035 for hydrogen is going to feel like what battery felt about 1 or 2 years ago, where everyone's like very, very convinced that this is going to happen. People are going to put money in, plow capital in there, and that might even cause a slight overproduction. But I think 2022, 23 battery is circa 2035 hydrogen, right? But that's like growth capital, right? For people who invest in Tesla, for instance, like you made most of your money before that, right? And then between now and the next and 2035, which is about 10 years, here's what you're gonna see. The next 5 years, by the end of the decade, you're gonna see maritime heavy duty trucks and the logistics applications have a major transition. Here's why. Internal knowledge, we already know that a lot of companies are actually willing to pay more money for logistics right now to decarbonize their scope 3 emissions because their consumers are demanding it. And as long as the logistics companies, so trucking, shipping, rail, aviation, are able to guarantee that things are actually moved in a carbon-free fashion, right? It's just that the technology is not there, you can't use a battery truck. But if you give someone that technology, they will do it. And they're able to fulfill those things at a slightly higher price point. And then the second one is in the next, between 2030 and 2035 is where I think things like hydrogen for grid and hydrogen for larger energy applications, where like you start generating just a lot of electricity, is going to start coming online. And then you'll see that really pick up past 2035, right? All the large capital projects will go in. And then after 2040, from 2040 to 2050, is when at that point, hydrogen is considered just mainstream industry. And then it'll just get commoditized and so on and so forth. And you're just doing capital projects left and right and finish up the decarbonization effort. So that's hydrogen usage in a nutshell. hydrogen production in the next 5 years, I think, are going to go into three major ones. So the first one is going to be in chemicals, because in chemicals, hydrogen is basically a high value input that you can tolerate a higher price for. Hydrogen for steel is going to be a big one. Again, the hydrogen for steel is a big one because there's also already demand for green steel. Again, driven by consumer demand, because you want a car that's made with green steel, right? And you can actually sell the steel at a higher premium. Therefore, it makes sense to make it, right? And then after that is green steel, hydrogen for chemicals, green steel, and then I think hydrogen for oil and gas might happen. That one's hard because most hydrogen applications in oil and gas are co-located. But that would be from 2025 to 2030, maybe 2033. I think 2035 onwards is when you'll see all the major hydrogen grid projects happen in conjunction with fuel cells. Even if you fix hydrogen production today, right? Now, why would hydrogen for the grid not happen overnight, right? And the answer is quite simple, because the turbine technology to even burn hydrogen and figure out the emissions is not figured out yet. And the fuel cell technology that's multi-megawatt to turn hydrogen into electricity, the same one we talked about, that's also not ready, right? So even if you were able to make hydrogen extremely cheap today, right, you would not really have the technology to turn it back into useful electricity, at least for a few more years. 2030 at the earliest, 2035 I think would be realistic. 2035 onwards, things will stabilize, then you just plow money into it, and then that's how you actually decarbonize. And then hydrogen will finally replace diesel and basically natural gas until by mid-century.
That's a really great summary. Thank you so much, Gary. This has been extremely enlightening. And I really appreciate you taking the time to explain things in a simple way for us.
Of course.
And thank you to Earthlings for joining us. We'll see you again on another turn of this beautiful blue-green space flower that we call home. Primary financial and production support for Earthlings 2.0 comes from Technica Communications, an award-winning PR firm amplifying breakthrough technologies of the future. Additional supporters include Greenlane, who is working to build a nationwide network of commercial EV charging infrastructure; Tigo Energy, a solar energy and software solutions provider focusing on commercial, industrial, and residential solar installations; Ampion, who is expanding renewable energy access for communities and Fortune 500 companies everywhere through community solar; 24/7 Solar, a next-generation concentrated solar power solution that's modular and can capture the sun's energy at a higher temperature than conventional CSP and store it in simple ceramic pellets; and the U.S. Biochar Initiative, who is increasing production and use of biochar in North America by developing markets, increasing awareness, and building community. And of course, our heartfelt gratitude goes out to you, our listeners, for your curiosity and dedication and showing up with us every week. Thank you so much. We do this for you. If you have a topic you'd like us to cover, or if you want to participate in our Pay It Forward guest model, please contact me at lisaann@earthlingspodcast.com. And you can search our entire archive on any podcast app as well as YouTube. And you can also go to earthlingspodcast.com and search our website there. Until next time, keep exploring and caring for this beautiful blue-green space flower that we call home.